So we have this problem wherein the scientists would like to know when the conians would reach 1,000,000. So we have this graph. At t equals to 0, the conians are at 100,000. At t is equal to 1, the conians are at 101,000. At t equal to an unknown time, the conians are at 1,000,000. We all know that this is a growth problem, so we set up the equation dx over dt is equal to kx. So we use variable separable to solve this. After having so, we would get dx over x is equal to k dt. Now we set up the limits. At t equals to 0, the population is at 100,000. At t is equal to 1, the population is at 101,000. So after evaluating that, we will get ln of 101,000 over 100,000 is equal to k. So now the value of k is equal to 0.0099. So now that we've solved for k, we can plug it into the equation. But take note, this has different limits because we're solving for t. Now look, at t is equal to 0, the conians is at 100,000. At t equal to an unknown time, the conians is at 1,000,000. Evaluating this, we will get an ln of 1,000,000 over 100,000, which is equal to 0.00995, which is k multiplied by t. Now, isolating t, we will get an ln of 1,000,000 over 100,000 over 0.00995. Now, evaluating that, we can get that t is equal to 231 months, or 19 years. Now we have this problem, wherein the conians have reached 1,000,000 and are slowly dying by 2% per month. We have this graph. We still don't know x sub 1 and x sub 2. But first we focus on x sub 1 to get k. To get x sub 1, we subtract 1,000,000 times 2% from 1,000,000. We get 980,000. Plugging this into this graph, we will get this one. By looking at this graph, we can see that this is a decay problem. So we set up the equation for variable separable. Dx over x is equal to k dt. Having this, we put in the limits. Now, at t equals to 0, the population is at 1,000,000. At t is equal to 1, the population is at 980,000. So now we evaluate this. We get ln of 980,000 over 1,000,000, which is equal to k. Now we get that k is equal to negative 0.020. So now we know the value of k. And we also know that the population is dying by 2% per month in a year. So we have t is equal to 12. Substituting these values into the equation, we have the limits at t is equal to 0, the population is at 1,000,000. At t is equal to 12, we're looking for how many the population will be. So now we have this. We have ln x minus ln of 1,000,000 is equal to negative 0.0202 times 12. Negative 0.0202 is k, by the way. So now we have ln x is equal to ln of 1,000,000 minus 0.0202 times 12. Evaluating this some more, we have ln x is equal to 13.57. Isolating x, we get e raised to 13.57. And now x is equal to 782,305, which is the population of the people after a year.
In the third problem, and we have this graph where we're solving for x sub 1 and t. X sub 1 is equal to 782305 minus the same value times 0.15 because the population is dying by 15%. We're going to find out that x sub 1 is equal to 664960. Plugging it into the equation, we're going to get that k is equal to negative 0.1625. Now that we've solved for k, we're going to plug it into this equation, but we're going to change the limits because we're solving for t. So after evaluating this, we're going to get ln of 1 minus ln 782305 is equal to negative 0.1625 times t. Isolating t, we're going to have ln of 1 over 782305 divided by negative 0.1625. We're going to find out that t is equal to 84 months or 7 years.